Hello, everybody. My name is Cesar Torres. I'm a faculty member in chemical engineering, and I will be starting the fluid mechanics module. I've been teaching this class for about 15 years, all the time that I've been here at ASU. Um, what we're going to do in the class, not only introduce the concepts of fluid mechanics, we're going to try to give you an idea of the most important equations that relate to fluid mechanics. And we typically divide this class into two. A macro fluid mechanics that relates to the transport of fluids in big equipment, how pressure drops, how fluid flows, etc. And then a micro component in which we're going to be using differential equations to determine the velocity or the properties of a flow in any time or space. And so we're going to start today with a section on fluid properties, which is probably, the beginning, definitions, and then we're going to go into fluid statics before we start moving fluids. So I will stop my video. We will do most of the presentations without the video on. So first, definitions. Obviously, what is a fluid? And basically could be defined as a gas, liquid, or plasma. And today and throughout the class of fluid mechanics, we're mostly going to be focusing on liquids. And there are certain sections on gases that we are probably going to skip for this module. You see that part of the definition is a material that will continuously deform when subjected to a shear force. So then let's define really quick what a shear stress is. And it's basically a parallel to a pressure in when there are two components that are moving parallel to each other. Great example is putting your two hands next to each other and feel that friction, that shear, that's a stress that happens in between your two hands. And in this case, you see a solid moving on top of a surface. You can think of this as a liquid on top of a surface. It will still have shear stress. Or you can think of it as two layers of liquid, one that is going a bit faster than the other. And then there is some shear stress associated to that as well. As I said, shear stress is force over area. It has the same units as a pressure. And then the second part of fluid mechanics is mechanics, which is the science focused on the motion of material bodies. So what we're going to discuss in this module then is fluids moving. But before we do fluids moving, we're going to do a little bit of properties and later fluid statics, so that then we understand details on how the fluid moves. So you will see in this figure here, I put below some YouTube videos that will show you this experiment of the rotating cylinder. It is basically an apparatus that is used to show what we call as the no-slip condition. What happens is that you have a rotating cylinder in the center, and this rotating cylinder is actually done by hand most of the time. So you have this handle here that allows you to rotate the cylinder. And then obviously the outside is not moving, so it's a fixed cylinder. And when you rotate that cylinder, what happens is that you create a velocity close to that rotating cylinder, and the velocity close to the fixed cylinder is zero. And that's basically what happens in the no-slip condition. I will let you look at the videos in more detail so you understand those concepts. But in general, what the no-slip condition states is that At a solid boundary, the fluid will have zero velocity relative to that boundary, which means that that rotating cylinder, if it's going at, say, 0.1 meters per second, the fluid next to it will be at 0.1 meters per second as well. But then the fixed cylinder is not moving, so the velocity is zero. So then you create this velocity profile that starts at zero and ends up at a high velocity close to the rotating cylinder. Now, we need to introduce a few more concepts. Pressure is one of them. Remember, the pressure is force over area, or force equals pressure times area. We will be using the concept of pressure throughout this module and in other modules as well. Important to note is that pressure is a scalar. We will go over it a bit later. The force that is applied is a vector, and you can see here that force, but once you calculate it as a pressure, it becomes a scalar. It has the same units as stress, as we said before. Now, density is probably one of those most important properties of the fluid that we will continue to use throughout. Density is mass over volume, right? Dense fluid tends to be heavier on the same amount of volume, and density is a function of temperature. And so one of the important things of doing fluid mechanics problems is that the first step is to calculate the real density at whatever temperature we have. The equation that we use in our book, which is Fluid Mechanics for Chemical Engineers by James Wilkes, that's the equation that is given, where the density at a temperature, any temperature, is going to be equal to a reference density, which we typically use 20 degrees Celsius because that's what we have in our table here, multiplied by that modifier 1 minus alpha T minus T0. T0, in the case of the values list, would be 20 Celsius. And then the temperature, T, is the temperature that you are operating at. And so that gives you a value of raw at a temperature T. And you see that the table has these values of alpha here. Those are the values that you're going to use for the equation. Viscosity. So the units of viscosity are typically a centipoise, which are equal to 0.001 Newton second per meter squared. You probably understand well what is a viscous fluid versus a non-viscous fluid. You can think of molasses or oil as viscous fluids and air as a non-viscous fluid, and everything in between. It is a value of how velocity, as you see there, how velocity develops from, say, a no-slip condition or a velocity of zero, and how quickly the velocity develops from that surface is how we define viscosity. Viscosity is also a heavy function on temperature. So you see here two equations, one for liquids and one for gases. You see the equation for liquids is logarithm of mu equals A plus B logarithm of T, where A's and B's are found in tables that are in the book. As you can see, this table for a few liquids. And then for gases, you basically use this equation that it's derived from the ideal gas law. You have the values of mu0 here, and you can do that calculation of mu at a new temperature. Now, velocity. Velocity is a flux. So basically, you are looking at a flow across an area, a velocity, how many meters per second, for example, fluid is going at. We're going to be using the letter U as to define velocity, and it leads to three important calculations. One is the volumetric flow rate, Q equals U times A, where basically U has units of, let me put it like this, of length over time, and then area is length squared, so that you end up with a volume over time, right? The mass flow rate is the same as the volumetric flow rate multiplied by density. So the density turns that volume into mass, because you have mass over volume for density. And then momentum. The momentum rate, which is the mass rate times the velocity, which can also be written as raw U squared times A. And we will get to those calculations later. And so those are a few examples of important fluid properties. And now we're going to start using some of those properties with fluid statics. When it comes to fluid statics, we are trying to do calculations of pressure, for the most part, calculations on the impact of that pressure, say, on structures like this. This is a picture of the Hoover Dam, one of the biggest dams in the United States. And so that information will be used, as you will see, when we start doing the mechanics part of the class. So the pressure at any point can be defined as the limit as the delta area tends to zero of the differential of force over differential of area. In other words, P equals dF dA. The English units for pressure is typically pounds per square feet or pounds per square inch. PSI is probably the most commonly used pressure unit in the United States. In SI, we typically use kilopascals, and know that a standard unit would be a pascal, which would be a Newton per meter squared, but it is a lot more common to work in terms of kilopascals. I already said that pressure is a scalar quantity. It has no inherent direction, and the force that it exerts is normal to the surface area. And I typically explain this normal to the area as you imagining yourself inside a pool. Imagine you go deep and you can feel the pressure of the liquid into your body. And it doesn't matter which way you move, you're still going to feel the same pressure. It's always inwards, right? It is normal to the surface area of your body. So that's how you feel pressure inside a fluid. And the same will happen whenever you have any system. Imagine that you have a little square underwater that will always have pressures that are inwards, and they are inwards in different directions depending on the surface itself, right? So we're going to talk about that in more detail in a few minutes. Now, when you are looking at a pressure, let's say that you want to calculate the pressure at the bottom of this stack of solids, and then we will compare that as we do the liquids as well. So the area at the bottom of this unit would be W times L. That's going to be the area. And I now need to know what is the force. And the force would be the mass times gravity, right? So a way to to calculate this is to say that the pressure, which would be force over area, equals rho GH. And I'll try to explain how we get into that equation. So rho is mass over volume, right? And we multiply by G, you see that I have mg. And I need to multiply that force, we need to divide that by area. So I have H here, and you see that the volume of this would be W times L times H, which means that the H's cancel, and I have now force over area. W times L equals area. The same happens in the liquid. You're going to say that the pressure at the bottom of this tank with a distance H would be rho, the density of that liquid, times G times the height of the liquid. And in a more differential form, you can now calculate forces acting on a cylinder of fluid where you have pressures, as I explained before, pressures coming from the bottom, coming from the top, and how those cancel out or are slightly different are essentially the way in which we calculate buoyancy in that system. Something that we are going to skip for now. So yeah, this is essentially the same equation, but now starting with a differential and then basically getting to this delta B equals minus rho G delta C, assuming obviously that the fluid is incompressible. Basically, it is a liquid, and the reason why it needs to be so is so that density is constant. We need a constant density in order to take it out of the differential DC. So yeah, so at any point in a fluid, then we would have that calculation where the change in pressure equals minus rho G delta C. So let's do a little example here of the problem. You're just supposed to calculate pressures at 0.2 and 0.3. The temperature is 50 degrees Fahrenheit. We have a change in elevation. You see that here says elevation 200, elevation 250. Those are really not that important for these calculations. The important part is the distance from the top of the liquid to the 2 points that we are supposed to be calculating it at. So, important thing that we typically assume that atmospheric pressure equals, so that P1 is going to be equal to 0. And that's what we call a gauge pressure. Whenever we assume that atmospheric pressure is 0, that's how we basically assume that it's a gauge pressure. What that means is that typically when you look at a pressure gauge, it is set at 0, even though it is at atmospheric pressure. So that's why it's called a gauge pressure. The first step on solving this is to turn this Fahrenheit into Celsius. And that's basically about 10 Celsius. Because we're going to use that equation that I showed you to calculate the density of water at 10 degrees Celsius. You will see that it is not, the W of water is 0.000207 to the minus 1 over degree centigrade. And you will see that the change in density is not that significant. The density of water at 10 Celsius would be 62.3. That is the one at 20 pounds per cubic feet. And now we're multiplying that by 1 minus 0.000207 degrees Celsius to the minus 1. 10 minus 20 degrees Celsius. You see that that will cancel the Celsius, and we have that the density at 10 degrees Celsius is 62.43 pound mass per cubic feet. So it did change a little bit. Now, I'm going to say that Now that we have that density, I can say, well, P2 equals P1, and I'm going to add now raw G 35 feet. And obviously, I can do the same for the next problem, just saying raw G 50 feet. So I'm just going to do 0.2. And so if I assume that P1 is 0, because this is going to be a gauge calculation, then P2 equals raw of water at 10 degrees Celsius, which we have here, G and 35 feet. Now, I'm going to go to the next slide so you can see it better. P2 equals 62.43 pound mass per cubic feet times 32.2 feet per second squared times 35 feet. And if you follow units here, you will see that I have, what? There you go. You will see that I have the units of pound mass on the top. I have 2 feet square, 2 feet at the top, and a feet cube at the bottom. So at the end, what we're going to have of units will be pound mass per feet second squared. That doesn't sound like pressure, right? And the reason is that in English units, we need to do a conversion. And that conversion is this one here that I'm going to put 1 pound force equals 32.2 pound mass feet per second squared. And that now gives you 2185 pound force per feet squared. That's a PSF. And we typically write gauge next to it so that people understand that this is a gauge pressure. So if you want an absolute pressure, you need to add the atmospheric pressure to it. So where does this come from? You see that 32.2 is actually the value of gravity. It's 32.2 feet per second squared. That's what is the same as 9.81 meters per second squared. In English units, it was accepted that a pound mass and a pound force would be the same number. And that would mean that whenever you have to calculate your weight as mass per gravity, because you're multiplying by gravity, then you have to divide by this conversion, which is typically called GC. In that way, the weight in pound force and the mass in pound mass are exactly the same. It creates some confusion and complications for us engineers when we are not really talking about weights and are more calculating pressures, etc. But that is how you do that conversion. Now, let's keep on now adding a little bit more complexity. If we now, in this static calculation, we have 2 fluids. One fluid and 2 immiscible fluids, right? One fluid has a certain density and the other fluid has a different density. So you see that we have outlined 3 heights, the top being C3, then a pressure, a C2 and a C1 at the bottom of the tank. Now, how do you solve this problem? It's pretty easy. You basically have to calculate first the pressure here at the interface between the 2 fluids. So you say P3 equals 0 because it's going to be gauge pressures. So this is going to be 0 at the top of the liquid. And then P2 will be the density of the fluid 2 times G times delta C. And then P1 will be P2 times the density of fluid 1 times G times delta C. So that you can put all that together as a calculation of calculating the pressure in this fluid and then calculating the pressure in this fluid and adding them up. You see? And the reason why I'm explaining this is that this is a very common calculation that is done for a manometer. So a manometer is typically a system that is used to measure either or originally the pressure differential between, say, this pipe, and that pipe might have a fluid moving, and a static system that is happening at the manometer itself. So you have a liquid that is typically denser than the fluid that you're working with and is immiscible in that fluid. And you have this differential as you see here. When you're calculating pressures on a manometer, you are trying to calculate the pressure inside, say, that tube or that pipe that has a flow. So then you say, well, we need to go backwards. We're going to start from here and go backwards to 3. And we're going to assume that 3 and 2, because they're at the same height, they have to be the same pressure. And then we know that P1 is going to be equal to 0 gauge. So that we know. Now we need to go to 4. So how do we do that? Well, I can do it forwards, and then I'll show you the equations backwards. So I can say that P2 is going to be equal to rho of the manometer, which is the density of that manometer liquid, G times that delta H, and that's going to be a value, a positive value, right? That's basically under. And that's going to be equal to P3. Now, the tricky part comes that 4 is a value higher than 3. And 4 also has a different liquid. Between 3 and 4, we have a different liquid. You see that this 3 is the interface between the two liquids. So that we're going to now say in this equation that P4 is going to be equal to P3 minus the rho of the liquid in the pipe, G and L. So you see that now, because we're going up, we have a lower pressure. P3 has to have a higher pressure. And P3 was already defined here. So we're going to now say rho M G delta H minus rho 1 G L, just for the sake of having two different values of two different heights, delta H and L. Now, an example that is in the book, and it's pretty complicated when you look at it, but you will see that the calculation becomes pretty easy once you understand what is happening. You have a U-tube, and this U-tube is typically used to determine the specific gravity, which is the same as density. When you're thinking about the specific gravity, say, of that oil, what we're saying is the density of that oil over the density of water. And that definition, and this is water at 4 degrees Celsius, where the density of water at 4 degrees Celsius is assumed to be 1,000 kilograms per cubic meter. So basically, if an oil has a density of 820 kilograms per cubic meter, the specific gravity would be 0.82. It is just dividing by 1,000. Now, in this problem, it says, based on the heights of the columns, find the specific gravity of the oil. And so you see that there is a little pocket of air here. And that pocket of air, we're going to assume that is negligible. Why is this the case? Well, if you look at the density of air on a table, you will see that the density of air is under standard conditions 1.29 kilograms per cubic meter. And the density of that water at standard conditions is 998. So half a foot, when you now consider that you're calculating pressures, and it's basically a raw GH calculation, half a foot of air is basically about 1,000 times less pressure than half a foot of water. And so this is almost zero compared to the rest. So we're going to assume that this is not here. And this is here just because it is useful to have some spacing between the water and the oil. And so how do you solve this problem? Well, it is important to note that in any of these problems, when you throw a horizontal line across a fluid, that horizontal line will always have the same pressure because it is basically at a certain equilibration. So this U-tube basically equilibrates so that the bottom of the tube has the same pressure on both sides. If, say, the left side has more pressure than the right side, then the fluid will move to the right side until it equilibrates and it's not moving anymore. So then we're going to assume that at the bottom of these two, we're going to have the same pressure. And the pressure on one side, on the left side, we're going to assume, so I'm going to call it P left so that we are clear. It's going to be raw of oil times G times 2.5 feet plus the raw of water times G times 2.5 feet. Sorry, times 1 foot. And that is going to be equal to the pressure on the right, which is raw of water times G times 3 feet. When we put them together, a few things that I can do. First, I can cancel this G by dividing by G. This raw of water, I can move this raw of water to the other side, so it'll be instead of 3, it'll be 2. And so that I have raw of oil times 2.5 feet equals raw of water times 2 feet. And if I now go to the definition, which I had put here, then the raw of oil over the raw of water is going to be equal to 2 over 2.5. Let me see where I can put this. S which is equal to rho of oil over rho of water equals 2 over 2.5. Obviously, out of space here. And that is equal to 0.8. Okay, that gives you a good idea of how to solve a static problem on different calculations of pressures using different fluids, etc. We're going to continue to do pressure calculations, but this type of problem with multiple fluids, etc., is something that relates more to fluid statics than fluid mechanics. I take here a little break from calculations and theory to give you this conceptual question and kind of a point for you to think about. So you basically have a conceptual question here of moving fluid from Tempe, Arizona. This is where we are at Arizona State University. We're going to move it to Flagstaff. Flagstaff, for those of you that are not familiar with, is about 2 hours from here in the mountains. So it is a big change in elevation between here and there. I'm assuming it has to be about 4,000 feet. What parameters or properties do you need to take into consideration when you are designing such a system? And if we had, a long conversation about this, there are many things that are very obvious. For example, the change in elevation. So you're going to have some sort of delta C that we're going to have to introduce. There is a change in temperature too. And that is somewhat important, but not as important as other calculations that we will have to do. There is a distance component, right? So you're going to have, typically that value is an L. And when you're thinking of this, by the way, I didn't explain, but this MGD is million gallons per day. Typically, that's a way of describing high flow or bigger flow rates in gallons per day, millions of gallons per day. And 500,000 gallons per day is a very small amount, by the way. Our city of Tempe probably consumes about 20 to 30 million gallons per day of water. So we have a distance of L, and now we need to start thinking about how we're going to move that fluid. Well, it turns out that, we are in Tempe. This is in Flagstaff. And when you are moving things at a higher elevation, the only common way to do it is with pipes, right? You need to pressurize that fluid in order for it to go up. So now we have considerations where we need to think about the pipe diameter, the pipe material, and it needs to be a material that resists a certain pressure. The pipe roughness, because that will determine later what is the frictional loss of that pipe. And, well, the pipe is not enough. You also need to put a pump to pump that up. So now I need to find a pump, and I need to have considerations as the pump power, the pump efficiency, among others. And so, to me, this problem is kind of a nice break into get you thinking that fluid mechanics is a very intuitive topic for you. You've been living in a fluid all your life. You have interacted with fluids in many different ways. You understand what friction is. You understand how to pump a fluid. What we are doing here is giving you the tools to do the calculations that are needed to do this type of design, engineering design. Um, and so hopefully that gives you an idea that whenever you are confused about concepts of fluids, you have to probably start by trusting your instincts on what it should be or how it should be, right? Let's start with chapter 2. In chapter 2, we have this balances section first. So we're going to go back a little bit on mass balances. We obviously do mass balances in fluids as well. We have typically a system that has streams flowing in and out, and you have an accumulation or depletion. For the most part, for this class, we're not going to have zero accumulation or depletion because most of our problems are pipes, and our pipes are always full. And so we are not going to deal much with accumulation or depletion. An important thing to consider is streamlines. And you can see here streamlines shown in this card. This is a way in which you can use a wind tunnel to determine the frictional losses of a sports car in this case. And what they do is that you have some sort of laminar velocity flow, and you introduce some powder into the air at specific points, making these lines. So you can see how those lines break or don't break as they touch the car. But this is a good example of how a streamline works. A streamline is basically a way in which basically where the fluid is flowing. The fluid that started here kept going straight, and you will find it at a certain later time going through that streamline. And this is a weird example of a streamline because you have a tank that is draining, and you can imagine that tank is draining, and you have streamlines following that drainage, right? There's two things that I want you to note in this system. First, that the streamline starts at the top, and that is because even though this tank might be draining slowly, there is a change in velocity at the top of that tank, right? The tank is draining, so therefore there is a flow, a velocity of that liquid coming down. The second part, and it's something that you have probably seen before in your house when you open the sink, you will see that you have a hole that is this diameter, but the stream is smaller. And that is what we call the vena contracta. You will see a little bit more of those details in the next class. That vena contracta happens because of the angles that this fluid needs to go as it goes into that orifice that is causing the drainage. So from here now we will talk about energy balances, and we will end up with an important equation, the Bernoulli equation. Now, when we think about energy, and there are a few different types of energy that I will discuss here. Kinetic energy, which we typically, let me put it here. Kinetic energy, which we typically is described as 1/2 mass times velocity squared. We're going to be talking about that one, of course. Potential energy, that mass, gravity times height, and then atomic, chemical, and electrical. And obviously, we do not care about atomic energy in this system. There are certain concepts of electrical energy when we start talking about pumps, but we're going to more or less introduce all of these as internal energy in the system. Now, when you put these together, and you kind of try to write an equation between point 1 along a streamline and point 2, and try to figure out how energy was conserved between points 1 and 2 of that of a streamline, you have an equation like this, where you have the internal energy of the system, you have a kinetic term, u1 squared over 2, and u2 squared over 2. You have so let me write it here, kinetic. You have a potential. Now you have a pressure related energy component. You have heat, which we are not going to talk about in this class. And on the other side, you have work. And that will be introduced once we add a pump or a turbine into our system, not right now. Difference between this equation and this equation is the lack of mass in it. You see? So the units of this equation is in energy per unit mass, or meter squared per second squared. So we will use this equation extensively over the next two classes. Another part that is important to include here is calculations of power. So we have right now, this is energy per unit mass. In other words, we are at joules per kilogram. Even though it's meter squared per second squared, meter squared per second squared is the same as a joule per kilogram. Now, if I now note that power is typically the rate of energy flow. So the unit is watt, which is equal to a joule per second. So now I need to turn joule per kilogram into joule per second. And the way that you do that is by multiplying by the mass rate, because that's kilograms per second. So now I'm going to have joules per second. Now, I take that equation, which is pretty big, and I make some assumptions. First, that there is no pump, so that work is gone. Second, there is no heat, as we said. And third, there is no internal energy to be considered. Now, when we do this, what we are assuming is a few things. No work effect, I kind of explained that. Steady flow, because we are moving along a streamline. But the important one is that the system is frictionless, because friction is part of that internal energy calculation. And so if our system has a lot of friction, we cannot use this equation, which we call the Bernoulli equation. It is one of the most important equations in fluid mechanics, mainly because it's simple and very easy to relate to. And by the time most chemical engineers finish their degree, they will remember this equation almost by heart. So it works along a streamline. Fluid is incompressible, so mostly for liquids. And the most important part is that you cannot have work effect, meaning that there is no pump between points 1 and 2 that you are analyzing, and that the system is frictionless, which I would argue there is no such system as frictionless. But if the system is such that the friction is not a big component, then you can use Bernoulli's equation. Not true for long pipes. It is not true for very small pipes either, like microfluidics, things like that, that always have a high friction component. So you have to be careful on how you use that Bernoulli equation. This is the first, a most simple system of Bernoulli is a tank that is draining. So the tank that is draining, similar to how we discussed before, in this specific example, we have values of 1 and 2. So where they're basically already telling us that we are going to do a balance of Bernoulli between 0.1 at the top of the tank and 0.2 at the exit of the tank. And it says basically an open tank drains, and the distance between the water and the drain is 10 meters. And with just that, we're supposed to find the velocity at the drain port. You see that we don't even know what's the diameter of this drain port. All we know is that there is 10 meters from here to the drain port. And that is enough for us to calculate a velocity. Now, if I go back to my equation, you see that I have 3 terms on each side. One that relates to pressures, one that relates to heights, C1 and C2, and one that relates to velocities, U1 and U2. And so we need to know what we're looking for is the velocity at point 2, the velocity at the exit. That's what we're looking for, which means that I should know all other 5 terms. Let's go look at it so you see. So first comes the pressure at point 1. And the pressure at point 1 is 0 gauge. This drain is open. So the pressure at point 2 is also 0 gauge. There is obviously pressures throughout this column of water. But at the exit, it is as soon as this opens into air, we can assume that this assumes the pressure of atmospheric. So then we don't care about the pressures anymore. Heights, where we can assume that C2 is going to be equal to 0. So that C1 equals 10 meters. Since we have a delta of 10 meters, then I can do it that way. And you see that that's 4 of them. And the 5th one that we don't know is the velocity at point 1. And we're going to assume, and that's true for any tank draining, we're going to assume that this velocity is almost 0. And you know it is not 0. I sort of explained to you 2 slides ago that it was not 0. But because the drain pipe is much smaller in diameter than the tank, then the velocity is almost negligible. So what does that mean? That I have now a Bernoulli, which is 1 U1 squared over 2 plus GC1 plus P1 over rho. Let me go back here so I write it the right way. U2 squared over 2 plus GC2 plus P2 over rho. And that I now say this is 0 and this is 0. And I say this is 0. And I say this is 0. So that U2 squared over 2 equals G times C1. Okay. That would mean that U2 equals to the square root of 2GC1. 9.81 meters per second squared times 10 meters. Okay. That is equal to 14.01 meters per second. As I explained before, this is a relationship of energy, and you see that with no knowledge of how wide this diameter of this exit is, we know that the velocity is going to be 14 meters per second. Obviously, the volumetric flow rate depends largely on whether that pipe is bigger or smaller. Okay, here's another example that is a little bit complicated. I have some of the slides here so that we can do these calculations. And I don't have to write them up. So we have a flow. The flow of this fluid is moving through a 0.15 diameter pipe, and then there is a reduction. Typically, this is called a nozzle, even though that in this case, you don't really have that much of a difference in diameter. And then you have the end of the pipe, so now this is open to air. You see also that there is a pipe coming up A, and that pipe is also open to air at the top. And that pipe is 3 feet in height. And it says water flows steadily from a pipe that is 0.1 feet in diameter. Determine the maximum flow rate to avoid water overflowing through tube A. And so I will set up, or at least set up the problem in this way. If there is no flow whatsoever, the velocity tends to zero, then this pipe A would be empty. You have to agree with that, right? It will just go down and drain to the exit. But as you start pumping at a faster rate, then you're going to start getting this liquid coming up, coming up, coming up, until it starts overflowing because the pressure is too high. So what is the pressure that we need to get that overflowing? That's basically what we are being asked. Now, we're going to use Bernoulli. And in this case, I put Bernoulli with a little twist. I divide it by G. This is just another way of expressing Bernoulli. This is what we call in terms of head, where all terms are in terms of, and all of the terms are in meters, or in basically length. It is the same equation. We just divide it by G. But whenever you're doing a Bernoulli, part of the question that you have to ask yourself is, which 2 points we're going to select? And you typically select points that are easy to solve. In this case, we need to select a point just below that value because that relates to the pressure that will cause that pipe to overflow. And the second point that we select is probably the exit of that pipe. And the reason for that is that I know that my pressure 2 is 0. I can also select the height to be 0, right? If I select the height at point 2 to be 0, then the point 1 is also 0. So now I have no height differential between these two. I have a velocity on point 1 and a velocity of point 2. I already had put values there, but I have a pressure at 0.1. I have a velocity at 0.1 and a velocity at 0.2, you see? And the problem with this type of exercise is that I now have two unknowns. By the way, side note before we continue is that the height here is 3 feet. The fluid before it overflows is stagnant in this pipe, which means that there is no flow and there is no streamlines along this pipe. Therefore, you cannot select, say, 0.1 here. There is no flow here, so you cannot do a Bernoulli between a point that is not moving and a point that is moving. So going back here, I'm trying to find a velocity, and I have two unknown velocities and a pressure. And you, as a side, you know that that pressure will be calculated from rho GH. I lost my capacity to write this down. I don't know why. So we need to do a trick here. And if you think about it, the velocity 1 and velocity 2 are related to each other because there is a mass balance. The liquid coming through 1, all of it reaches 2. And therefore, the flow rates are the same. Q1 are and Q2 are the same. We put this here so you kind of have it at the back of your mind. So if the flow rates are the same, these were our definitions of flow rates, velocity times area. So the velocity times area 1 equals velocity times area 2. Because area equals pi over 4 d squared, then I can put the definitions of these two and cancel the pi over 4 so that I have this correlation, u1 d1 squared equals u2 d2 squared. And that then allows me, by just knowing the two diameters, to calculate a correlation between velocity 1 and velocity 2. Velocity 2 will be now 2.25 times velocity 1. And now that we have that, I can easily come here and plug that into u2 squared. Keeping in mind that this is u2, and I'm going to square it. Therefore, I not only need to square u1, I need to square the 2.25 as well. So this is how it looks. I'm going to say that I go back here, that P1 over rho G is equal to 3 feet. You see, I put P1 equals rho G times 3 feet, and it cancels the rho G. And so I have now only 3 feet. U1 squared over 2 times 32.2. That's gravity in English units. And then, as I said, 2.25 u1 squared, making sure that we squared the 2.25 as well. That gives me a velocity of 6.9 feet per second, and then I can calculate a flow rate of 0.12 cubic feet per second. That was basically what was asked for, a flow rate. Since I have U1, I need to calculate it using A1, when that basically is with the 0.15 foot diameter pipe. And so we'll stop here since it's been about an hour, and we will continue this discussion of Bernoulli and then expand to other concepts of momentum balances in the next class.